Welcome to the pre-recording of lecture 19 of computational geometry. So this is a lecture on expected cost and degenerate cases. Short title. The complete title is Expected Cost and Degenerate Cases of the Randomized Incremental Algorithm to solve the planar point location problem. A very long sentence, but I will try to make this lecture self-contained. So in this sequence of lectures, 17, 18, and 19, we are considering the important problem to locate oneself on a map. In the age before smartphones, you had an actual physical map with you, and you were trying to look around in your immediate surroundings where you could pinpoint yourself on the map. In the age of smartphones, the smartphone will do that for you, and in some sense, the purpose of this entire sequence of lectures is to explain why this can be done very efficiently. We have explained the problem in lecture 17. I will summarize this in the next 4 slides. We also have seen that we can solve this with a data structure. And we have a randomized incremental algorithm there. The first main point of this lecture is to explain how the expected costs of the randomized incremental algorithm is very favorable, leads to an efficient implementation. And in order for the exposition to make it somehow less complicated, we had to make some assumptions. So the second goal of this lecture is to indicate how we can remove those assumptions and how we can deal with so-called degenerate cases. Okay, what's our problem? Well, we have coordinates of a point and we have a map. Can we situate the point defined by those coordinates? Can we situate that point on the map? Know where you are is the title of the section. Mathematically, we have a planar subdivision. We have n edges, so n is a little n, but it's a big number in this lecture here. It will determine the size of the input. The input also is our query point, qx, qy. There are 3 cases. We can have that we are in the open field, we are in a face of a subdivision, as is in the first case here. As you can see, you are in a square or in an open area. You are either on the road, on an edge, or you are on an intersection point, on a vertex. So this is the mathematical formulation. Given the coordinates, can you find where you are? Or can actually a computer solve that problem for you? We do this with a refinement of the subdivision. So we have here an example at the left of a map. We have roads, intersection points, and open spaces. What we do is we place a bounding box around it, so the area we consider is finite. And we add vertical extensions to all the vertex points. So in red are the extensions which run not all the way through. That was our first idea of lecture 17, but that turned out to be rather expensive as far as storage cost goes. Instead, we have vertical extensions that go to the edge above, which could be the bounding box, or the edge and the edge below. And you can see where the word trapezoidal decomposition, so the trapezoidal decomposition arises because our faces in this map are in general trapezoids. So the last four lines are in some sense a definition of a trapezoidal map, but also an algorithm that runs in linear time. So making all these vertical extensions depends on the number of edges, the little n of the previous slide. So for every edge, we have two endpoints. So we are going to, so this is a double loop, which should always make us a little bit wary or uncomfortable, but it's not an n square algorithm. Okay. Um, the corresponding data structure to use the height, or whether you have to go north or south, first you have the first coordinate, which allows you to situate yourself left or right, but then you have to go up or down on the map. And we have a directed acyclic graph, which was introduced in the previous lecture. So in some sense, this slide summarizes the building of the directed acyclic graph that is associated to the trapezoidal map. So let me indicate how this is used. So suppose that your query point would be in the face with A2. So A2 is at the left of P1, so it's in the left child. It's to the right of P2, so we go to the right child, and it lies below the segment S2. So the directed acyclic graph, it's not a tree because we will store every trapezoid. So E is a trapezoid which occurs twice as a leaf. We only store it once. So this is why we don't really have a tree, because we do not want to duplicate. So the leaves could probably be exponential. But we don't have this exponential cost. So that's important to realize here. We will see that the storage cost is linear also in the number of edges. Actually, we proved this also in the previous lecture, that the total storage cost is linear for this entire data structure. So we have the map, our first data structure, and then we have the directed acyclic graph, which is the search structure. Okay, one more slide, and perhaps I should now emphasize something. So we do have a randomized algorithm. So here, what does the randomized mean? Well, our input segments, they are permuted. So we have the permute pre-processing step that precedes the algorithm. So the algorithm starts with making first a bounding box, initializing the decomposition with that bounding box, the top and the bottom edge, and also the uh, vertex points. We have our construction of the vertex, vertices in the directed acyclic graph. That's the D. It's an incremental algorithm. We are adding the points one after a time. So we have the first important character n. That will be the dimension n. We will measure everything with respect to n. But the other character that will be used frequently later in this lecture is the I, not the I of I, but the I from the incremental loop counter. So each time we locate the trapezoids that the new segment will intersect, we update the map, and then we update the directed acyclic graph. So the correctness of this algorithm follows from the loop invariant. At every stage, we have a correct trapezoidal map, and we have a corresponding directed acyclic graph that allows us to efficiently locate any point in this data structure. Okay, I'm 10 minutes in, summarizing the previous two lectures. Let me now state the main theorem that we are trying to prove today. So again, why does randomization work? Well, why is it needed, first of all? It could be that our tree or our directed acyclic graph, if it resembles a tree, if the depth is logarithmic in the number of line segments, then we have a logarithmic cost for our search. And this you can see, which is where we have the n log n that we like. However, there will be cases, and that was one of the exercises of last time, you can actually not avoid, if you have a deterministic algorithm that fixes the order of the line segments, you cannot avoid that you have actually one long tree, one branch essentially. And that would give a quadratic time algorithm. However, the idea is that the very bad cases, they are little insignificant in numbers. So you would need to have very bad luck each time over and over again with every every new I segment, you would need to have very bad luck. So that's kind of the intuition why random algorithms work. But we will try to make this a little bit more rigorous. So here you see the expected cost. So the algorithm is expected to give you a trapezoidal map and a search structure computed in n log time. You have the loop, the main loop n, and then you have the logarithmic search that happens each time. The search structure is also expected to be linear in and the search structure, we actually indicated that the trapezoidal map is linear, but we actually also want that the search structure, the directed acyclic graph D, is also linear in N. So if the search structure is balanced, then the expected query time is logarithmic, which is quasi-constant. Okay. We will prove two lemmas, and then they will give the result. So the lectures are actually structured top down. So the proof, I will introduce some notation, and here I'm actually stating that the first lemma will give us that the query time is logarithmic, and the size of the search structure is linear. What does this make is that the size of the structure determines also the amount of work that we have to do. So remember, we have seen output sensitive algorithms. If your output is quadratic, then also the time to make the output will also be quadratic. So this is here where the size comes in. So we have the O of I, we have a proof by induction. So the I here runs over all the line segments that we are inserting into the data structures. On average, we have, so you can see if this lemma is true, then actually the main theorem follows because we have the O of I that is on average divided by I. So we have actually a constant. And actually the search determines the factor here. So we have the n log n that comes out. The O of n is because of the initialization. So we are going to permute things. And we've seen in a very earlier lecture that you can make a permutation in linear time. So this is the startup cost. Okay, you could also sometimes sort all the points on their x coordinates. So that would also be an n log n startup cost, which is fine. So this is so the n is also needed to build a bounding box. So you will need to go through all the line segments to find the coordinates of your bounding box. So you need to run through all your line segments to find the highest endpoint, the lowest endpoint, the left and the right. So that's another startup cost that you have. Okay, so in some sense, if you believe the lemmas, then you believe the theorem. So the theorem is plausible if the two lemmas are true. Okay, outline of the ideas in the proof. So here is the top-down reasoning. First of all, again, point 0 here. Why is it's important to have the expected here? So there is the expected running time, and this is on average, and expected is not a bad word here. So whenever you run the algorithm, the expectation is that it is logarithmic. Now that doesn't mean that if you are very unlucky, and also you could also say that if you build maliciously a permutation that is not good, then actually you will have, again, your structure that will be long. So that's the worst case scenario. 3n is an upper bound. Why is that 3 there? Well, if we have a segment, so here is the probability that a segment intersects. So we have a trapezoid that was created, so a trapezoid of our query point. So we have to replace a trapezoid when the line segment intersects it. And the probability, so the expected value, so xi is the number of nodes that you add. So you may add on average 3 of them, and that depends on the probability. It's actually 0 or 1, but this is where the 3 comes from. Oh, that goes through the previous lecture. Then, what is the sum of all these probabilities? Actually, the expected value of the number of nodes. Well, this depends on the harmonic number. And now that comes completely out of the air. So I say this is a top-down. I will explain why the harmonic numbers come in. The harmonic numbers are important on their own right to study. So we've seen logarithms. They are a discrete sum. So here you see the definition of the nth harmonic number. They are related to the logarithms that we will make precise. But in the proof, we will have to make sure that the number, the expected total number of nodes, is actually 12 times the harmonic number, which is often very odd because the expected number, the average, it seems like we are dealing with probabilistic things of game. Anything can happen. That is true. But the average is actually a very precise number. So it is the harmonic number. So in some sense, every proof that is worthwhile contains an element of surprise. So the harmonic numbers are kind of surprising that they come in here. It's also kind of surprising that we can come up with such a sharp answer. Very precise, exact for the expected value. Okay, what is the expected size? Again, why do we need expected? Well, that is the worst case. If we are really unlucky, so let's say that we save the largest line segments for last, then we have meticulously built all our trapezoids, and then with one stroke of the pen, we are going to build one road that intersects all the trapezoids. Highly unlikely to happen, but you could be unlucky that with the ith segment you are intersecting all the I trapezoids that you have already. Could happen. So that leaves you then with a quadratic post. Um, Even as the number of leaves is bounded by, this is then another, so the comma is kind of related to the uh, size of the trapezoidal map. So we actually proved a bound on the number of trapezoids. So that is the number of leaves. But still, the search structure could require that size. All right, we have the eye. So why could the search structure be so large? Because we have the inner nodes. So the inner nodes is related to the number of new leaves. So we have the delta that depends on the trapezoid in the new subdivision. Si is what you have there, and it depends whether the line segment intersects it or not. So if you take the average, so you divide by 1 over I over all the line segments, so you do this with 0 and 1 quantities, then you have this expected number of line segments, the expected number of new leaves, I'm sorry, that this is OI over I, which is actually a constant. So given the notation here, and this may take some time to digest here, if you take the average, so why do we have the 4 coming in here? Um, there is the size of the uh, number of trapezoids that you could have. So you have the 3n plus 1 sitting there. So for all the segments in the subdivisions over all the trapezoids, you have this quantity 1 over 0. And that is expected to be proportional to I. Averaging makes that as a constant. Okay, so this is the skeleton proof of the lemmas. Let me elaborate a little bit on this because there are things that are definitely at this point not clear. So when you have to replace a trapezoid, we have this, and actually I should have changed this into I instead of once. So in the worst case, you have actually 3 nodes that are added with every segment. So therefore, 3n is actually an upper bound on the path length. So there was an exercise in a previous lecture where I was inviting you to build um, a sequence of line segments where the next line segment would always intersect the last trapezoid that you added. So in the incremental construction, we replace the leaves, and the leaves are replaced when you have a line segment passing through that. So this is where the 3n comes from this upper bound. So we are exploiting here also the linearity of the expected value. The expected value of the sum is the sum of the expected values, which is useful. Okay, so there is the tree that comes in here again. So we have the probability pi. So you can see I'm giving the proofs a little bit upside down in the wrong order. So we had this probability pi, and we had the 3, at most 3 nodes are coming in. And then we have the data structures. So the fact that what is the PI now, the probability? Well, it is the probability that a trapezoid is newly created. So the trapezoid that is in the ith subdivision on the ith trapezoidal map is actually not contained in the I minus 1. So it is a newly created one. Also important to realize that the new trapezoid, they actually are all adjacent to them. And here you see the number 4 coming in. What are the items that you store in each iteration? Okay, so here's the technique that we applied earlier. So this is the backward analysis. So we are looking back. Um, the probability that if you have a trapezoid created in the ith iteration, it is related to where the new segment, the ith segment, is located. So where it's going to be? Well, it's going to be either at the top or the bottom of the new trapezoid. Also, that's one way, or it also can be related to the left or the right. So that's the alternative. So there are 4 different ways how the number 4 can appear. So this is the explanation for the number 4. The 4 different ways in which a segment can manifest itself in a new trapezoid. And it's either or. So it's either, so one of these 4 cases must happen. Okay. So we observe actually the probability that this happens is 1 over I. So assuming that for all the segments, they have equal probability here. For equal probability that there will be the top, the bottom, or that the left point is an endpoint, is the left point of the trapezoid, or is the right point of the trapezoid. So this gives us the formula for the probability that we have a new trapezoid. So again, should probably say here this is the PI. So this is the probability that we actually have a node on the search path created of with the query point at the ith iteration. So the capital PI is here defined in words, but numerically we have a bound on that probability, and that is 4 over I, and that is obtained reasoning backwards. So we have a new trapezoid in the ith iteration, then it's related in 4 different ways to the new line segment, the SI. Okay, the harmonic numbers, where come they now in? So that was kind of magical. Well, we have now that, what I should say that, why did we need the PI? Well, the PI was the expected value of the number of nodes added at iteration I. So that is the linearity that is used here. So I could have squeezed in one more equality. The expected value of the sum is the sum of the expected values, and we have this 3 over pi, and pi is bounded by 4 over I, and this is where the number 12 comes in as 3 times 4. Okay, so this gives us 12 times the sum over 1 over I. So we actually have known already the geometric sum, the sum over the first I integers. There's also the reciprocal values of these i's. So the sum over 1 over the i's, one of these guys. So 1 over i's, they are known as the harmonic numbers. So they are very important. The textbooks write them with capital H, even though there is no Mr. Harmonic. But they are traditionally, checked Wikipedia as well, they are defined by the capital H. They are very important. We can plot them even. So if we plot them, so here is a plot, 1 over 2, 1 over 3, 1 over 4, you could think of somehow hyperbola. So we only have the positive branch, we think positively here, but there could be a mirror one, it could be another branch there, although it's not right to think about a hyperbolic here. But one end goes to infinity, 1 over 0, and actually one end goes to 0. But it's not hyperbola. Sorry, I misled you. It's related to the logarithms. So logarithms here. Um, why is this? Well, from calculus, we know that if we take the antiderivative of 1 over x, we get the natural logarithm. So for complexity way, and that's something that certainly must have discussed in algorithms or even already in data structures, the base of the logarithm doesn't really matter. So that is absorbed in the big O. So the natural logarithm here, if you think continuously, that is indeed natural. In the if you think in a discrete manner, then we always write log, and we'd always think about the binary logarithm. But for cost consideration and the big O, they are the same. Okay, so this is it. So in some sense, I go too fast. One should actually first start with the harmonic numbers, then define the probability, see how the harmonic numbers come in, and then essentially get to the proof of the lemma. So this is the bottom-up uh, delivery of the proofs. But in some sense, the top-down provides the surprise element of the harmonic numbers. Important, the bottom line, the average path length is there, logarithmic in the size of the input. So the number of line segments is n. Okay, so a suggestion is to backtrack, but the forward integration, what I said, is referring to the integration rule, how it is known in numerical analysis. In calculus, you must have seen Riemann sums. And here you can relate Riemann sums to the numerical approximation of 1 over x. So consider this definite integral, and the first part of the exercise, perhaps I can actually solve it. So the first part of the exercise is actually that you make those drawings here. So you have to show that 1 over 2, so you have here essentially 1. So this is 2, this is 1. So the first 1 over 1 is actually the area under this box. The 1 over 2, so this is 1 over 2 here, we are at 3, 3 minus 1 is 1. But we always have 4 minus 3, the 1 in the numerator stays the same. But the denominator is always the reciprocal of the beginning point. So that's essentially it. You make the drawing and you say that the approximation for the integral is the sum of the areas under all these boxes. So in some sense you explain what is a Riemann sum. So that is a numerical upper bound for the area under the blue line starting from 1 up to n. So here, if you're a little bit economical with your work, you can take n equal to 4. If you can prove it for n equals to 4, then you can go with proof by induction. And explain the induction step. That is making one new box. Okay, so this is how the Riemann sum relates to the harmonic number. So in the limit that you can actually see that the two are going to be the same. So the difference between the boxes turned out to be quite considerable. But as the n gets larger and larger, the logarithm of n, well, logarithm of infinity, you shouldn't really be doing this. But you can see, and this is where analysis comes in again, that it will go to infinity. So the harmonic numbers diverge. However, you can, it's kind of strange, well, not strange, is that there is a, well, it is strange, that the limit as n goes to infinity, the difference between the harmonic numbers and the natural logarithm is a constant. Uh, Run experiments here. And it may converge pretty terribly. If you look at Wikipedia, there is a name for that constant. Uh, if you want, say, 3 decimal places, how large should n be? That's also one way to get a handle on this. So logarithms, so there's a final comment here, logarithms in general in this course give us a good feeling. Now, if you have converging processes, it may not be so good if you have logarithmic convergence. Logarithmic convergence means that in order to gain one extra decimal place of accuracy, you may need to do the same amount of work. Very, very, very costly. Is this the case here with these harmonic numbers? Okay. Um, the main part of the lecture is over, but let me say something about degenerate cases. And in some sense, degenerate cases means that there are no vertical segments. If you think about the real world, we cannot have a road that goes straight from south to north. Perhaps in some European villages, not that much of a concern, where people think in round roads and things like that. But in realistically engineered, well-designed city plans, we would have essentially have all straight vertical line segments. Okay, so that was an assumption that we made. Also, no vertically aligned vertex points. That was also very good, because we've shown that if you would have more than 4 adjacent trapezoids, that could only occur if vertex points had the same x-coordinates. Again, very unrealistic to make in a modern city plan, where the number of intersections going from north to south are nicely lined up. Okay, then there are the other cases. What if query points lie, if you allow vertical extensions? Well, what if the query points lie on them? What if the query points lie on the line set? So in some sense, the cases that we have dealt with so far are actually only always assumed that our query point was in a face. In some sense, not so realistic if you think that on a plane, so we would work idealistically with lines that have only one dimension, so they have no thickness. So you could also say, well, this is natural. Our points, they would be considered disks with also an area, so they would always overlap in the face. So in some sense, the assumptions were not so bad to take as well. Okay, here is the idea. So instead of, so if you have a map with strict north to south, you would start to distort your map a little bit in what is known as a shear transformation. So you tilt the y-axis on a small angle. So actually it corresponds to adding to every x coordinate an epsilon times the value of the y coordinate. And the epsilon for people in numerical analysis could actually be, it could be that it's just of the size of the machine precision. So you notice it, but it's like a rounding error. You actually don't notice it. And we will work with that also symbolically. So here it is. So why does it first work? So if we do this, you can actually see it works because the epsilon is here on the picture actually quite large. But you can see that after this transformation, that indeed the 2 points P and Q no longer have the same x coordinates because their y coordinate is different. So that's important here. We used this argument also actually also when we were using the composite numbers. The composite numbers was a little bit more dramatic because with the composite numbers we were exchanging both of them. Here actually we only changing the x coordinates. So we see it that it is effective, but now can you also work it out algebraically? And here is then the algebraic explanation. So you kind of see that the B1 and the B2, so the points are not the same. So one point is lower than the other. So by convention, we had that P is the lower point. The argument works also the way if you would swap the points. But because the points are not the same, one is lower than the other, the x coordinate is different from each other. Again, it's done symbolically, or if you are a numerical analyst, you could say that it is in the rounding error. So we have different rounding errors, and it actually doesn't really matter which one is different from the other. Although if you're more higher up, you have more round off. You could see it like that as well. Comparisons are done symbolically. So you can actually say symbolically, we say that P is more to the left because it is lower. That's what it is. That's the convention. Okay, what now about the query points? We had the X nodes, the Y nodes. What happens if the query point lies actually exactly on a vertical extension? What do you do then? Do you go to the left or do you go to the right? So you don't know. I mean, you still need to locate it. It's at a vertical extension. So, but we actually don't know what happens. Okay, um, you can only have equality if the query point coincides with the endpoint. Verify that above statements. That's an exercise. For the Y node, we are comparing heights. What happens actually when the query points lies on the segment? So we actually have to then show that if the transform point lies on the segment, then that's fine. Then actually we have found the location of our query point. We are on the road that is represented by that segment. And in some sense, I was pausing a little bit with exercise 2. So if we have equality, then we have the endpoint to which the x-coordinate belonged. So that's then also done. So we have located the point. So we have actually found that the query point corresponds to the endpoint that made the X node. So you can think as a programmer now that if you store your data structure, if you have that test, you have the equality also with the shear coordinates, then you have equality, then it must be that your query point corresponds to the endpoint to which the X node belongs, either the left or the right. Okay. Whew. Uh, the main result is that we can solve the planar point location problem in n log n time by constructing the trapezoidal map and the search structure. Notice that actually we can do this construction uh, offline. Typically, there is always construction going on wherever you go, but typically these maps are pre-computed. So they're computed in n log n expected time. The main point here is that we no longer have to rely in general position because of the shear coordinates. So we can determine our position where we are on the map in quasi-constant time, in logarithmic time. So that is the main importance for the users of these electronic maps. Um, you can have 1,000,000 segments, and I don't know if there might actually be, you can have afford 1,000,000 segments on your maps, but 1,000,000 is 2 to the power 20. Your query time will still be expected 20 steps. 20 steps that you have to do, and you can locate yourself on the map. Okay, so this concludes chapter 6. So that's actually the summary, the last theorem. The exercises are kind of inviting you to reflect a little bit. The exercise 1 came rather late. There were many exercises in the previous lecture, so perhaps after the first 4 slides, if you got confused, look at the exercises of the previous lecture. The goal of these lectures is also that you get familiar with the textbook and that you get a handle on solving the exercises in the textbook. Okay, so this closes chapter 6. In the next lecture, we will go into Voronoi diagrams. So we are concluding the first 6 chapters. We are in the 6th week of the course, getting in towards the middle of the course, the 7th week, where we will study Voronoi diagrams.